Hello, Physics 1 students. Today we're going to be going over Prelab number 5, the topic of which is vectors. So before we really dive into vectors, I want to make sure that everybody's on the same page with regards to the unit circle and the coordinate plane. So with the unit circle, I wanted to review that at the positive x-axis, you would be at 0 degrees. At the positive y-axis, you would be at 90 degrees. At the negative x-axis, you would be at 180 degrees, and at the negative y-axis, you would be at 270 degrees. Okay, now these are going to be really important because, as I'm going to mention in a little bit, vectors have both magnitude and direction, and the way that we'll be expressing the direction is with angles. So it's important that you know how the unit circle works in order to draw your vectors in the correct locations. In a similar vein, let's come over here and look at the coordinate plane. So you're going to be calculating x and y components of your vectors. So that will also aid you in drawing your vectors. So if you have positive x and y components, you know that they're going to be in quadrant 1. If you have a negative x component but a positive y component, you know it's going to be in quadrant 2. If you have both negative x and y components, you know it's going to be in quadrant 3. And if you have a positive x component and a negative y component, you know it's going to be in quadrant 4. Now, I'm not going to go over this because it's not really relevant to the pre-lab, but I put this slide in here just as a quick reminder. If you do have to do any conversions between radians and degrees, this is how you would do it. All right, so let's review all of the trigonometry. So last week we talked about SO and CA. So we talked about sine, that's the opposite over the hypotenuse, and CA, cosine, that's adjacent over hypotenuse. This week, as I promised last week, we are bringing TOA, so that's tangent, into the fold, and tangent is the opposite over the adjacent. Or if you're thinking about in terms of what we talked about last week with projectile motion, this would be your y term over your x term, right? Because in this instance, we had our y term here, right? Because that's on the opposite side. This is our vertical side. And then our x term was on the adjacent or the horizontal side. And then, of course, the hypotenuse was whatever our initial velocity was. So this week with vectors, we're not going to be focusing on just velocity, but rather more broad applications of vector quantities. So we're going to bring a lot of forces in, but you will still have some vector quantities like displacement and velocity that you've already calculated and worked with. All right, well, now that we've reviewed a little bit, let's dive right into vectors. So if you recall me saying before, vectors have both magnitude and direction. So let's start talking about how we would go about finding the magnitude of a vector. So as you can see right here, we're going to be using Pythagorean's theorem, which is this formula down here. So that's c squared is equal to a squared plus b squared, where c is your hypotenuse, and then a and b are your adjacent and opposite sides. Okay? Now, if we come over here and we look at this example right triangle, this is implying that we already have our opposite or our y component and our adjacent or our x component, but we don't have the hypotenuse, which would be the magnitude of the entire vector. So that's where we're going to be using Pythagorean's theorem. We're going to use Pythagorean's theorem in order to solve for the hypotenuse, which is the magnitude of the vector. Now let's talk about the second aspect of a vector that makes a vector, and that is direction or the angle of the vector. Okay, so right here you can see that there are 3 different ways that I could calculate my direction. And the reason that I put arctangent first is because a lot of times you're going to have the x and y components, and if all you need is that angle, you're not going to go and bother calculating the hypotenuse, right? Because you probably don't have the magnitude already. Usually when you do these problems, they either give you the components or they give you the magnitude and direction, and then you need to find either the components or the magnitude and direction. Okay, so in order to not do a bunch of extra work, I would recommend using arctangent when you're given the components. So that's going to be your opposite over your adjacent side, or your y component over your x component. And you can see if we use inverse tangent, we get 31.6 degrees. And then if you look to the right, you can see that if we use arc sine or arc cosine, we get exactly the same thing. The only difference here is the fact that arc sine and arc cosine are using the hypotenuse, or they're using the magnitude of the vector. And if that's something you haven't calculated already, and it would be a waste of time to calculate that quantity because the question isn't asking for it, then the easiest way to calculate it is arctangent. Now, this convenience isn't without its pitfalls, because if you remember back when you were probably learning about tangent for the first time, if you were to have a right triangle in the first quadrant, and let's just say, for example, that the opposite side is +4 and the adjacent side is +3, well, the angle that you're going to get for calculating that right triangle, your angle theta, is going to be exactly the same as if you were to have a right triangle in the third quadrant that has an opposite side of -4 and an adjacent side of -3, right? Because if we divide a positive number by a positive number, we get a positive number. And if we divide a negative number by a negative number, we get a positive number. And if you recall, the magnitude of our adjacent and opposite sides would be exactly the same. So the decimal quantity that's produced when we divide y over x is going to be exactly the same. And unfortunately, your calculator does not know the difference. So it's up to you to pay attention to the components and know, hey, I have two negative components. I shouldn't be getting an angle between 0 and 90 degrees. All right, so now if we put it all together, what are vectors? Vectors have magnitude and direction, right? And so as we talked about, the way that we find magnitude is we use Pythagorean's theorem and we solve for the hypotenuse. And for the direction, we typically are going to use inverse tangent or arctangent to find the angle, because more than likely we'll have been given the components and we don't want to go through the trouble of calculating the magnitude for a problem if we don't have to. So this slide is just a reminder of what I already mentioned to you about being careful when you're using tangent. Remember that the calculator doesn't know the difference between the fractional value that it gets between the first and third quadrant and the second and fourth quadrant, so it's your job to be paying attention to your components and knowing what the calculator does not know. For example, if you have two negative components, so both x and y are negative, and you get 60 degrees, you need to know that you need to add 180 degrees to that angle because it should be in the third quadrant since both of your components are negative, but the calculator doesn't know any better, and so it's just calculating that reference angle. So one more time, because it's really important, make sure that you're drawing pictures and paying attention to the signs of your components. If your components are not adding up to what your calculator is giving you for the angle, add 180 degrees to that angle. All right, so a couple vector terms that are going to be really important: resultant and neutralizer. So the resultant is going to be your net force. That means you're going to add up all your x and y components of all the vectors in the system, and this sum is going to give you the x and y components of the resultant. And I did bold and underline this. That's because sometimes students will add up the magnitudes. Never ever add up the magnitudes. Only ever add up all the x components and all of the y components. It is not correct to add up the magnitudes. There may be a couple situations where you're on the x or y axis where it doesn't matter if you do add up the magnitudes, but most of the time that's not going to be the case. So best practice, add up the components. All right, to find the magnitude of the resultant, calculate the hypotenuse of a right triangle formed by the sum of all the x and y components. To find the direction, this is assuming that you don't already have the magnitude, use arctangent. If you already have the magnitude, then don't go through the trouble of trying to figure out what your calculator doesn't know, right? And just use sine or arc cosine, and that will come out correct. But of course, if you are using arctangent, double check that the angle is in accordance with the sign of your x and y component. And if you've drawn a drawing, which you should, double check that it's lining up with the vectors that you've drawn in your drawing. All right, the neutralizer. So this is what needs to be added to the resultant so that the forces sum up to 0. The way that you get the neutralizer is you multiply the components of the resultant, so your net force components, you're going to multiply them by -1, okay? And this will give you the components of the neutralizer. The neutralizer is the force, as I already mentioned, to be added to the system for static equilibrium. So this means when you sum up all the forces with the neutralizer included, you're going to get a net force of 0. The neutralizer has the same magnitude as the resultant, but it's going to be in the opposite direction. So it's going to be 180 degrees from the direction of the resultant. You can see that I've summarized that here. Neutralizer is equal in magnitude to the resultant, but it is opposite in direction. Okay? So now I'm going to walk you through a quick example of a vector problem and show you how you might want to set it up. And so right here you can see we have Maggie and Jack. They're playing tug of war. And Maggie is pulling with a force of 8 newtons at 165 degrees, while Jack is pulling with force components 6.2 newtons in the positive x direction and negative 2.3 newtons in the negative y direction. Who wins tug of war, and how do you know? So the first thing that we're going to do is we are going to define what would constitute a win for Maggie and what would constitute a win for Jack. So if our resultant has a positive x component, that means Jack wins, right? So that means he is going this way with the toy, right? And that's how we define the winner of tug of war. If Maggie wins, that means that our resultant is going to have a negative x component, okay? So that would mean that the rope toy is moving this way, right? Which would constitute a win for Maggie. So first things first, I cannot stress enough how helpful it is to have drawings for these problems. So draw what you can. It's a little bit harder when you're given magnitude and direction to do a drawing, but just estimate as best as you can. You can see I tried to draw an 8 Newton long arrow here at approximately 165 degrees. Then for Jack, which you have the components for, that's a lot easier. So I can look and see just a little bit past 6, so 6.2, and then about a third of the way down past 2. And I just put a little dot there, and then I draw my arrow to meet it. The next thing that you're going to want to do is you're going to want to make a table of known information and use it to calculate unknown information. So you want your table to include your vector name, your horizontal component, your vertical component, your magnitude, and your direction. Okay, so for these vector problems, those are the 4 quantities that you're going to have to calculate. So make sure that those are included. All right, so for Maggie, we were given the magnitude and direction, so 8 newtons at 165 degrees. For Jack, we were given the components. The horizontal component is positive 6.2, and the vertical component is negative 2.3. So this here is an optional step, so I called it step 2A. If it helps you outline reference triangles for your vectors, it might help you visualize the math a little bit better, especially if it's been a while since you did trig. So you can see over here I just drew a reference triangle for Maggie. So once I compute this, which I know I haven't done it in the table yet, but once I compute the values, then I would label my reference triangles with the values that I computed. And then over here, obviously, I already have the values. But like I said, this is an optional step, so you do not need to do this. Only do it if it helps you to solve the problem. All right, so step 3 is to solve for the unknowns. Make sure that you watch your signs and you verify all calculations with your drawing. Okay, so for Maggie, they gave me the magnitude and the direction, so I'm going to find my components. So to find the horizontal component, I'm going to do my hypotenuse times cosine of my angle, so 8 cosine of 165, and I get negative 7.7. For my vertical component, I'm going to do my hypotenuse times sine of my angle. So that's going to be 8 sine of 165, and that gives me 2.1 newtons. Now for Jack, I was given my components and I need to find the magnitude and the direction. I don't actually have to find the magnitude and direction to solve this problem, but I am solving the magnitude and direction because it is really good practice. Okay? So if this were an exam, though, you would probably want to skip finding the magnitude and direction since it's not relevant to the solution you're looking for. All right, but to find the magnitude, you're going to take your two components, so your opposite and adjacent sides, you're going to square them and take the square root, right? We're using Pythagorean's theorem. So we take our adjacent side, our opposite side, we square them, take the square root, we get 6.6. So that is the magnitude of this vector here. And then we look for the angle. So we use inverse tangent of our y component over our x component, or our opposite side over our adjacent side. And automatically our calculator tells us that this is minus 20.4 degrees. So now we need to think to ourselves, is that correct? So what is a negative angle? A negative angle means that we are going clockwise, right? So that would be this way. And so negative 20.4 looks like it's about right, okay? So if you don't want to report it as a negative angle, you could report it by doing 360 minus 20.4 and get 339.6, but it is equally correct to do negative 20.4. Keep in mind, if you are doing a positive angle, I didn't mention this before, but you're going to be going counterclockwise, right? When we did the unit circle, right, we went to 0, 90, 180, 270, 360, right? So if you see the letters CCW, that means counterclockwise, so that's indicating the normal avenue of constructing a positive angle. So once again, you can see that I'm doing extra work here. But as I mentioned, we are going to do extra work for this problem because we're not in an exam setting and this is good practice. So really, if this wasn't an exam setting, I would only calculate this guy here, right? Because that would be giving me the answer to the question, okay? But if you come up here and you look at step 4, how we're going to compute the resultant. So to find the x and y components, we want to sum up the x and y components for our forces. So that's going to be from Maggie and Jack. Then we're going to want to find the magnitude and direction. And to do that, we use Pythagorean's theorem and arctangent respectively. All right, so let's get started. To find the resultant to find the x component of the resultant, we're going to add up the forces from Maggie and Jack, right? So negative 7.7 plus a positive 6.2, that gives us a negative 1.5. So right there, we would actually be done if we were in an exam setting, right? Because this is a negative x component, so we know that that means that Maggie won. However, we are doing practice right now, and so we are going to move on and calculate the vertical component, the magnitude, and the direction. Okay, so to calculate the vertical component, we're going to add our forces up. So we have 2.1 plus a negative 2.3, and that sums to a negative 0.2. To find the magnitude, we use Pythagorean's theorem. So for these two summed forces here, those are our components of our final resultant vector, right? So we take negative 1.5, we square it, we add it to negative 0.2, we square that, we take the square root, and we find that that's about 1.5. Then we find the direction, so we use inverse tangent. We're going to take our y component over our x component, and we find that this is equal to 7.6. Now, this should raise some alarms for you because we see that both of our components are negative, right? And if we look at our picture, we can see that this is in the third quadrant. Well, the third quadrant means that the angle should be between 180 and 270. 7.6 is not. 7.6 is in this first quadrant. So that means we need to add 180 degrees to this angle. So once we add 180 degrees to it, we get 187.6. 187.6 satisfies our quadrant requirement, right? That the angle lies between 180 and 270 because the resultant is in the third quadrant. And so now we're good. All right, so now we're really doing some serious bonus work because we're going to calculate the neutralizer, but of course we know that for the purposes of solving this problem, we do not need to attempt finding the neutralizer at all. Okay, but as I mentioned, we're doing this for practice, and so we're doing it anyway. All right, so the neutralizer, as we mentioned before, is going to have components that have the opposite signs to the components for the resultant. So you can see here the resultant is negative 1.5, so that means the neutralizer is positive 1.5. The vertical component of the, or the y component of the resultant is negative 0.2, so that makes the neutralizer component a positive 0.2. Now you can see if we were to add up a negative 1.5 and a positive 1.5, those would sum to 0, and if we add up a negative 0.2 and a positive 0.2, these would sum to 0, and that's exactly what a neutralizer is, right? This is the force that you add to the resultant that makes the net force 0. Now with the magnitude and direction, well, the magnitude, you can see I didn't do any math here, and that's no accident. We know that the magnitude of the neutralizer is the same as the resultant, right? So I looked at what the magnitude of my resultant was, and it's exactly the same for the neutralizer. However, for the neutralizer's direction, that's going to be different, right? Because the neutralizer is equal in magnitude, but opposite in direction. So that means the neutralizer is going to be 180 degrees away from the resultant. So you can see I took the angle from our resultant, which was 187.6. I subtracted 180 degrees. That way I get the opposite direction. And so I got that the angle would be 7.6 degrees. And remember before, when we did this calculation for the resultant and we got 7.6, that wasn't correct, right? Because we had two negative components, so it's supposed to be in the third quadrant. But here we have two positive components, so 7.6 is absolutely right. So this is just a quick little summary of my recommended steps for solving vector problems. So the first thing that you want to do is draw whatever you can. Then you want to make a table of all your known information. You're going to use that known information to solve for your unknowns, probably just your relevant unknowns rather than all of the unknowns like we did for this example. And that may include computing your resultant and your neutralizer. But of course, you can't calculate your resultant and neutralizer until you have the components for all of your forces in your system, okay? Because remember, you can never ever add magnitudes. You only ever add components. All right, so now that we have a good overview of vectors, let's go ahead and get started on the pre-lab practice problems. Now, if you haven't already attempted the pre-lab practice problems, I'm going to recommend that you pause the video here, work through all the problems on your own, and then once you've finished them, check your work and your answers with the video. All right, pre-lab practice problem number 1. The hypotenuse of a right triangle is 7 meters, and the side opposite to the angle theta is 5 meters. What is the value of cosine theta? So the first thing that I want to mention is that there are two ways to solve this, okay? And neither way is better than the other. Both of them give you exactly the same answer. So whichever one you think to do first, just stick with that one. All right, so the two ways that you could solve for it is you could find the adjacent side using Pythagorean's theorem, or you could find the angle using inverse sine. So I'm going to work through the Pythagorean's theorem method first, and then I'll work through the angle method second. Okay, so here you can see I've rearranged Pythagorean's theorem to solve for what we want to solve for, which is the adjacent side. So you can see the adjacent side is equal to the square root of our hypotenuse squared minus our opposite side squared. Now I plug in our values. So we have 7 squared minus 5 squared, and we're going to take the square root. And we get that the adjacent side is equal to 4.9 meters. Now, we know that cosine of theta is just a ratio between the adjacent side and the hypotenuse side. And so we plug in our value for the adjacent side, we divide by the value for the hypotenuse side, and we get 0.7. Okay, and that's our answer. Now the other way that you could have done this is by using inverse sine. So we know that the angle theta, this guy right here, is equal to the inverse sine of the opposite side over the hypotenuse. Okay, so that means 5 over 7. Take the inverse sine, we get 45.58 degrees. Cosine of 45.58 degrees is also 0.7. All right, pre-lab practice problems 2 and 3. So these kind of go hand in hand, as you can probably see from my image here, and even on the pre-lab practice problem sheet, they're grouped together. So the first thing that I'm going to do is I'm going to draw myself a picture. Okay, so this is my hypotenuse. They told me vector A has a magnitude of 8 meters. So there we go. This has 8 meters. And it's at an angle of 45 degrees counterclockwise from the x-axis. So remember, counterclockwise, that's this way. That's a positive angle. Okay, so this is about 45 degrees. And then I'm going to want to find AX, so my x component of that vector, and AY, my y component of that vector. So number 2 is specifically asking for AX, so I'm going to solve that first. Okay, so AX is equal to A cosine theta, as we've established in the previous lab. AX, of course, when we plug in our values, that's going to be 8 cosine of 45 degrees, right? Because the hypotenuse times cosine of theta is going to give us that adjacent side. So we do that, and we get that AX is equal to 5.66 meters. Now number 3, we want to find the y component. So we know that AY is equal to A sine of theta. And so we plug in our values. AY is equal to 8 sine of 45 degrees. And we also get that the y component is equal to 5.66 meters. Once again, we have problems that were grouped together on the sheet, so I kept them together for the pre-lab. So problems 4 and 5, we want to know for vector B, what is the magnitude of vector B, and what is the direction of vector B. And you can see up here we have the prompt. They tell us vector B has components -3 in the x direction. Okay, so -3 in the x direction and -7 in the y direction. So -7 here. So I tried to do an illustration of what vector B might look like. So since number 4 is asking us for the magnitude of vector B, I'm going to start with that. So we're going to use Pythagorean's theorem to solve for the magnitude. So we know that these components are the adjacent and opposite sides. Okay, and we know that to find the magnitude, we're essentially finding the hypotenuse. So we plug in our values. We know that x is -3. We know that y is -7. We're going to square them, take the square root so that we can get the hypotenuse, and we get that the magnitude is equal to 7.62 meters per second. And that is our final answer. Now for number 5, we're going to use inverse tangent of our y component over our x component to solve for the angle. Okay, so you can see here, we're solving for our angle, right? And we're using arctangent to do it. We plug in our y component, divide by our x component, and we initially, from our calculator, get that the angle is 66.8 degrees. But then, of course, we come over here and we look at our handy-dandy drawing and we see, hey, that's not right. That's in the third quadrant. Or you could be looking at your components and see that both of them are negative, and you know that could only occur in the third quadrant, which makes you think, my angle needs to be between 180 and 270, and 66.8 does not satisfy that. So what do we need to do? We need to add 180 degrees. Okay, so we add 180 degrees, and that gives us 246.8 degrees. That is, in fact, in the third quadrant between 180 and 270, and so that is the correct answer. So now we get to problem number 6, and now we have a different prompt up top. So given vectors R1, which is equal to 1.4 meters at 30 degrees, and R2, which is equal to 3.4 meters at 90 degrees, and the equation of a new vector, capital R, which is -4R1 plus 1.5 R2, what is Rx? So the first thing that I'm going to recommend is that you draw a picture. So illustrate where R1 and R2 are, and then you can proceed to make yourself a table and record your given information. Okay, so you can see over here in the table, I've written down my magnitude of R1, my direction of R1, my magnitude of R2, and my direction of R2. And then you can see I've also filled in all the names of the vectors for the vectors that I'm going to need to calculate things for. All right, so I realized that a bunch of math just appeared that wasn't there a second ago. And don't worry, we are going to go through all of it before we answer the question, what is our x? All right, so let's start out at the top. So at the top here we have R1, and if you remember just a second ago, we had just the magnitude and the direction. So I took the liberty of solving for the components. The way that I did that is for the x component, I multiplied the hypotenuse by cosine of theta. So in this case, 1.4 cosine of 30 degrees, and I got 1.21. Then for the y component, I did the same thing, just this time I used sine, so 1.4 sine of 30 degrees, and that gives me 0.7. Now for R2, if you remember, we just had magnitude and direction, and so once again, I solved for the horizontal and the vertical components. So for the horizontal component, I took 3.4 cosine of 90. Well, we know that cosine of 90 is 0. 0 times anything is 0. So, of course, it should come as no surprise. Our horizontal component is 0 for R2. And if you look at the drawing, this makes sense too, right? It's literally just along the y-axis. Then for the vertical component, we have 3.4 sine of 90. Well, we know sine of 90 is 1. 1 times anything is itself. So we end up with 3.4. Okay? Moving on. So now we get into the meat of the problem. Now we're finding the components that make up capital R. So we're going, as you can see here, this says negative 4R1. So what we're going to do is we're going to take the components from R1 and we're going to multiply them by negative 4. So in R1, for the x component, we had 1.21. So we're going to multiply 1.21 by negative 4. This gives us negative 4.84. Then we're going to take our y component, which was 0.7, multiply that by negative 4, and that gives us negative 2.8. Now you can notice to the right, I just wrote in not needed. I didn't bother to calculate these, and I would highly recommend that you do the same thing in quiz and exam settings, because you just don't have time to calculate information that's not needed to give you the answer to the problem. And I did the same thing down here for R2. Okay, I just calculated the relevant information. Speaking of which, let's carry on. So the horizontal component of 1.5 R2, it should come as no surprise that since this says 1.5 R2, we're going to just be multiplying the components of R2 by 1.5. Okay, so 1.5 times 0, right, because that was this guy here, is 0, and 1.5 times 3.4 is 5.1. So remember, problem number 6 asked us what is the x component of capital R, and so that's what I did here in blue. So the x component of capital R means I'm going to add up these components right here, okay, because these are our x components, but I only want these last two rows here because capital R is negative 4R1 plus 1.5 R2, right? So that's just these guys here. So I add negative 4.84 to 0, and of course, not surprisingly, that gives me negative 4.84, and so that is my answer. Negative 4.8 meters is my x component of capital R. All right, number 7. So this time we want to find what is our y component. So if we take a look down here, all we did was we took our y components for these last two rows, right? For the negative 4R1 and 1.5 R2, we added them up. So negative 2.8 plus 5.1, so that gives us a positive 2.3. So Ry is equal to a positive 2.3 meters. Problem number 8. What is the magnitude of R? Okay, so now that I have the components, I drew in, you probably saw it just a second ago appear, I drew in capital R since I know where it is now. And so now I'm going to find my magnitude of R. I'm going to use Pythagorean's theorem. So you can see I used my two components, my x and y components. I take the square root of negative 4.84 squared plus 2.3 squared. and I get 5.36. That is my final answer for the magnitude of R. Prelab practice problem number 9. What is the direction of R? Okay, so that's what I did down here. So I used the inverse tangent of my y component over my x component, and I got an erroneous angle from my calculator, which was negative 25.41. Cannot stress the importance of drawing pictures, right? Because I would know that that should be in the fourth quadrant, right? Negative 25.41. But I can see clearly that R is in my second quadrant. So I know that I need to add 180 degrees to my angle. When I add 180 degrees to it, I get 154.6. I know that it's in the second quadrant, as I mentioned, and so it needs to be between 90 and 180, and 154.6 fits the bill, so that checks out. That is the correct answer. All right, pre-lab practice problem number 10. So this time we want to solve for C. We just want the x and y components in the following equation. R1 plus 2R2 plus C is equal to 0. So now when I see an equation like this, automatically my brain thinks, okay, R1 plus 2R2, that's my resultant. C, that's my neutralizer, right? Because if I add up all three of these, I get 0. So that means that I have to have some kind of neutralizing force in there. Of course, the next thing that I want to do is I want to draw a picture. Okay, so here I've drawn all my relevant vectors. I have R1 here, I have R2, I have 2R2, I have R1 plus 2R2, and I have C. Okay, now when I started this problem, of course, I wouldn't be able to draw in a lot of these vectors, but as I went along, you can see I did the math over here, I was able to fill in my picture. Okay, you'll also notice that for R2, I put a strike through it because I wanted to make sure that I didn't use that row, because you'll notice that we want 2 R2, so 2 times the components of vector R2. Okay, so we already went through how to do R1 and R2, so I'm just going to briefly go through how you calculate 2R2 and then the resultant R1 plus 2R2. So how do you calculate 2R2? Well, that just means that we're multiplying the components of R2 by 2, right? And so up here we can see that the x component was 0, so 2 times 0 is 0. Up here, the y component was 3.4, so 2 times 3.4 gives us 6.8. Then for the resultant, we have R1 plus 2R2, so that means we want to add up our components for R1 and 2R2, so we have 1.21 plus 0. That gives us our x component for our resultant, which is 1.21. Then we want to do the same thing for the vertical components, so we have 0.7 plus 6.8, and that gives us 7.5. Then the problem, remember, was asking us for C, which I decided to call C my neutralizer. So that means that the components, the x and y components, are going to be the same as the resultant, but they're going to have the opposite sign. That way, when I add them up, they sum to 0. So I have, for the resultant, I have a positive 1.21 and a positive 7.5. So that means my neutralizer components need to be a negative 1.21 and a negative 7.5. And indeed, you can see when we report the answer, that's exactly what we have. We have a negative 1.21 and a negative 7.5. No, I can't tell you why they wanted to report it in this really complicated vector fashion, but this is one of the many ways that you could report the answer. All right, so we're coming down the home stretch here. Problem number 11. So problem number 11 has a new prompt, so I'm going to take a minute and read that now. A horizontal ring is being pulled in 3 directions by force vectors F1, F2, and F3. The forces balance, meaning the vectors add up to 0. So as soon as I see that in a word problem, that the vectors add up to 0, immediately what I think of is that we have a resultant neutralizer relationship. So I give my first 2 vectors that I have information for, I call them my resultant, and then I take my remaining unknown vector and I say that this guy is my resultant. Now the next thing that I want to do is I want to record my given information in my table. So for F1, they told me that the x component is a positive 4. So you can see I recorded a positive 4. My y component is a negative 8, so I recorded a negative 8. For F2, my x component is a negative 3, so I recorded a negative 3. And my y component is a negative 6, so I recorded a negative 6. Now, just like the previous problems, when we're finding the resultant, we're going to sum up our horizontal and vertical components. So I'm going to start with my horizontal components. So I sum up my positive 4 and my negative 3. This gives me a positive 1. For my vertical components, I sum up my negative 8 and my negative 6, and this gives me a negative 14. Now the last step to do is to find the components, which of course is what we're looking for, right? We're looking for the components of F3 for problem number 11. So all I have to do is flip the sign on my resultant components, and that will give me my neutralizer components. So my resultant, I had a positive 1 in the x direction. So for my neutralizer, I have a negative 1 in the x direction. For my vertical components, I had a negative 14 in the y direction. So now I have a positive 14 in the y direction. So now that I've established what my components are, I can go ahead and draw myself a picture. That way, later on for problem 12, when I'm verifying my direction, I can make sure that I'm in the right quadrant. Okay, but this is pretty much it. I have my components now, and so the answer to number 11, F3, is equal to negative 1 in the x direction and positive 14 in the y direction. All right, we made it. Last problem, problem number 12. So for problem number 12, we want to find the magnitude and the direction of F3, okay? So as you can see, I've already done the math, but we're going to go through it together, okay? So to find the magnitude, we're going to take the square root of our two components squared. So x component, that's negative 1. We square that, add it to our y component, that's positive 14. We square that. Take the square root, we get 14 is our magnitude. Then for the direction, we're going to use inverse tangent of our y component over our x component. And when we plug it into the calculator, we get negative 85.9. Okay, so now this is where either you're going to want to look at your components or you're going to want to look at your drawing and verify if this is the right angle or not. And so I'm going to come over here to my drawing because I'm more of a visual person. Okay, and I can see that this should be in quadrant 2. So my angle should be between 90 degrees and 180 degrees, but much closer from the drawing to the 90-degree portion, right? Well, if I look at this angle, it's a negative angle, right? So that means it's going clockwise, and since it's 85.9 degrees, it coincides with exactly where the resultant is, right? So that's not correct for the neutralizer. That means I need to add 180 degrees, which means the correct angle is 94.1 degrees. Okay, so there's our answer. We have F3 is 14 newtons at 94.1 degrees, or if for whatever reason, if you wanted to express it as a negative angle, much more complicated, but it would be negative 265.9 degrees. And that is the final answer. So now if you'd like to stay tuned, I'm going to go through a quick review of projectile motion. But if you feel comfortable with projectile motion, feel free to stop the video here. So if you recall from last week, we went over how to calculate the components of the initial velocity of a projectile. So this is assuming that we're given a problem and they tell us that the initial velocity is, I don't know, 10 meters per second at 45 degrees above the vertical. Okay, so what we want to do is we want to break it down into its x and y components. Okay, so VOY, which is this guy over here, and VOX. The reason that we want to do this is because we're going to be using position and velocity equations in the x and y directions, and so velocity or VOY and VOX are going to be parts of these equations, essential parts of these equations. So it's important that we know how to calculate them correctly. Okay, so just a quick review. To calculate the x component, we're going to take whatever that initial velocity value is. My example was 10 meters per second. So we're going to multiply that by cosine of our angle, which in the example I just said is 45 degrees. So it would be 10 cosine of 45 degrees, and that would give us the x component of our velocity. Then for the y, we are going to do pretty much the same thing, just this time we're going to use sine instead of cosine. So we will take the initial velocity, multiply it by sine of our angle, and that will give us the y component of our initial velocity. So we went over this slide last week as well. This is just a summary of your typical projectile motion equations. So position in the x-plane, typically this is just going to be Vox times t. You're not going to have an acceleration in the horizontal, nor are you going to be given an origin, so a starting position in the horizontal. So you can just write both of those off as 0. You're going to probably have position in the y-plane, and typically you're going to have all 3 variables, but sometimes you might get lucky and you might not. But for position in the y-plane, typically AY is going to be gravity, right? That's your acceleration in the vertical. VOY, we just went over on the previous slide how you calculate that when they give you the initial velocity. So VOY times T plus whatever your starting height is, right? Your starting vertical position. Then last but not least, another really important one is velocity in the y-plane. So Vy of t is equal to Ay times t plus Voy. Okay, so your vertical acceleration times t plus your initial velocity in the vertical. And of course, we use this equation all the time when we're trying to figure out what time an object, a projectile, reaches its highest point, right? We set this equal to 0, and then we calculate what the time is. So I didn't go over this slide last week because we were going to do real live examples of each of these pointers, but since this is a review, I am going to go through each of my bullet points here. So for finding t-turn, okay, so we just mentioned that, finding the time that you're at your highest point, you are going to set Vy of t equal to 0, right? Because up at the highest point, the velocity, the vertical velocity is equal to 0. And then we just solve for t, and that'll give you t turn. If you're solving for y turn, so what is that position at the highest point in the y direction? We're going to, of course, plug t turn into our y of t equation, right? Because the y of t equation is telling us what the position is at a given time. So if we plug in t turn, that's the time it's at its highest point. So this will give us our y turn. Now for t final, so this is the time that the projectile strikes the ground, we are going to set y of t equal to 0, right? That's assuming that you're setting the ground as y is equal to 0 meters, right? Okay, so once you set it equal to 0, you're going to solve for the roots, okay? Depending on whether or not you had a starting height, one of the roots might be where you started from, or one of them might be before the motion even started. Either way, the root that is the correct one is going to be your positive one, okay? All right, that brings us to range or x final. So to solve for the range, you're going to plug t final, which you solved for here. You're going to plug t final into your x of t equation, or your x position equation, right? So typically, as I mentioned before on the other slide, your x position equation is probably just going to be Vox times t, so your velocity in the x direction, your initial velocity in the x direction times the time, right? And specifically the final time here, right, that you calculated this way. All right, so that's how you find the range. If you're trying to find the initial velocity for a horizontal shot, then you are going to solve for t final like you did up here, okay? Then you're going to use the x of t equation to solve for Vox. So in this case, if you're trying to solve for VO, they're going to give you the range already. Okay, so you will already have x final. So you solve for t final, and then in your equation, which typically would be x final is equal to Vox times t final, you would rearrange it so that you're solving for Vox, because that's going to be your unknown this time. So when you rearrange it, you get that Vox is equal to your range, or x final, divided by t final. All right, this is my last review slide, and this is just kind of a reminder of how you can draw these pictures so that you can best keep your data organized. Okay, so when you're doing a projectile motion problem, you're going to want to make sure that you include all of your variables. You're going to want to make sure that you include your signs, okay? So the signs, that's going to depend on your origin. So that's right here. I'm defining this right here is 0, 0. Up from there is going to be positive. To the right of there is going to be positive. And then the opposite directions, of course, would be negative. Then I'm going to define my starting time as 0 seconds, and I'm going to define my starting position in the x direction as 0 meters. Now, you can see over here I've labeled once again that my horizontal axis is doing double duty, so it represents both time and my position in the x direction. Okay? Then over here, still on the horizontal axis, if you've been given the range or x final, you would fill that in. If not, then just fill in where it is and then write a little question mark next to it because you haven't solved for it yet. Same thing goes for T final, so this is the time the projectile strikes the ground. This is important to include in your drawing as well. Then if we come up here by our actual projectile, we have our starting height, so whatever they tell us the starting height is, that's y naught. Then our acceleration, probably going to be gravity, and since I defined up as positive, ay, our acceleration in the vertical, is going to be negative 9.8 meters per second squared. For our horizontal, most of the time, they're not specifically going to tell you that there is an acceleration in the horizontal. And if they don't mention that there's an acceleration in the horizontal, then you know that it's probably 0. Okay? Then up here, if we take a look at our velocities, they probably gave us an initial velocity, they gave us the magnitude, and they gave us the direction. And then it's up to us to find the components. So VOY is going to be our vertical component, and we find that by doing VO sine of theta. And it's good to include this in your drawing as well as the appropriate sign. You can see that the arrow is pointing upwards, so this would be a positive velocity in the y direction. Then down here, if we look at our adjacent side, that's going to be the x component of our velocity. And so you can see this is how you solve for your x component. Again, another good thing to have in your drawing with the correct sign associated with it. And you can see from down here, that would also be positive. And then last but not least, if you're going to be asked about your t turn or your y turn, so the highest point of your motion, it's good to label that as well. And then once you have this picture drawn, it doesn't hurt when you've done your calculations to actually graph your parabola that you find for your y position. Typically, you're not going to have a parabola, you're going to have a line for your x position equation. But for your y position equation, it can be really helpful to look at a graph and double check your work. That way, you can see if you've calculated t turn and y turn, if you are actually in the right ballpark. So that's all I've got for Prelab 5. Best of luck on the quiz.